The workup of your chemical reaction simply refers to the isolation of the product from the reaction mixture. This means that your product should be free of both solvent and spent reagents. This implies no purification.
Purification of the organic reaction product is carried out subsequently. The choice of your workup procedure should always take into account the properties of the required product. Stagehand?
If the product is a liquid, you may isolate the crude product by distilling off the solvent. If the product is a solid, you may isolate the crude precipitate by filtration. Most often, however, water or ice water is mixed with all of the ingredients in the reaction and the product isolated by extraction into an organic solvent using a separatory funnel. This video explains simple workup procedures, especially that using the technique of solvent extraction using a separatory funnel. Transferring a solute from one solvent to another is a process called extraction. When an organic compound is shaken with a mixture of immiscible solvents, an organic solvent and water for example, the compound will distribute or partition between the two solvents according to its solubility in each. When the two liquids have separated again into distinct layers, the concentration of the compound in each layer will be defined by its distribution coefficient. Workup of a reaction by extraction uses a separatory funnel to isolate the product. Other equipment needed includes a ring clamp, a receiving vessel, usually an Erlenmeyer flask, and a long stem glass funnel. A separatory funnel is made of thin glass and therefore should be handled carefully. The most important part of it is the stop cock, which may be either glass or Teflon. Close the stop cock and place the separatory funnel in a metal ring. Get into the habit of placing an Erlenmeyer flask under the separatory funnel as soon as you have put it in its ring support. Check that the stopcock is closed, then pour the mixture to be extracted and the extraction solvent into the separatory funnel using a long stem glass funnel. Remember to allow sufficient space in the funnel to mix the liquids. If there is a large volume of liquid to extract, then carry out the extraction in batches. As a general rule, never fill the separatory funnel more than 2/3 full. First, hold the funnel round the top. Lift it clear of the supporting ring and swirl it gently to just mix the layers and help prevent pressure buildup. After swirling, return the separatory funnel to its support and insert the stopper. Vigorous swirling and shaking is required to effectively mix the solvent layers. To do this, hold the funnel in the following way. Hold the body in one hand and keep one finger over the stopper at all times. With the other hand, hold the funnel around the stopcock, keeping the stopcock in place like this, or like this, so that you can open and close the stopcock quickly with your fingers. Practice your grip on an empty separatory funnel. Lift the separatory funnel clear of its support. Adjust your grip and invert the funnel. To release any pressure buildup, immediately vent the funnel by opening the stopcock. Most extraction solvents are volatile, and vapor pressure causes a buildup of pressure in the funnel. For this reason, never attempt to extract hot solutions, as the increased vapor pressure may cause the solvent to blow out of the funnel. And remember, when doing extractions with carbonate or bicarbonate solutions which may generate the gas carbon dioxide, pressure release is very important. After the first venting, close the stopcock, swirl the inverted funnel for a few seconds, then vent it again. If excessive pressure buildup is evident, repeat the swirling venting process until it diminishes. Then, and only then, shake the funnel. From 5 to 10 vigorous shakes are adequate to establish equilibrium between liquids. Do not shake too vigorously, or an emulsion may form. Vent the funnel at least once, and when shaking is complete, make sure that the stopcock is closed, then return the separatory funnel to its support stand. The organic and aqueous layers will separate into two visible layers in the separatory funnel. Remove the stopper, and if any organic material is stuck to the side of it, rinse this back into the funnel with a few drops of the extraction solvent using a Pasteur pipette. Before running off the lower layer through the stopcock, be sure which layer is which. You may be able to tell by the relative volumes of the two layers, or from the known density of the organic extraction solvent. Is it more dense or less dense than water? A practical method is to add a few drops of water to the separatory funnel to see which layer it goes into. Here the water drops are miscible with the upper layer. Having located the interface between the layers, hold the funnel on both sides of the stopcock to ensure that the stopcock does not fall out, and arrange the funnel so that the tip of the stem touches the side of the Erlenmeyer flask. This reduces splashing. Then open the stopcock slowly. Do not allow the liquid to run out too quickly, as this will cause a vortex to form which will drag some of the upper layer through as well. When the lower layer is almost drained, close the stopcock and swirl the separatory funnel to knock down any drops of liquid that are clinging to the glass. Open the stopcock slowly and carefully run off the remaining lower layer into the flask. Close the stopcock and gently tap the funnel stem to dislodge any last drops into the Erlenmeyer. The upper layer remaining in the separatory funnel should be poured into a clean Erlenmeyer flask through the neck of the funnel rather than run out through the stopcock to avoid contamination by the material from the lower layer remaining in the stem and the stopcock. Be prepared to remove the stopcock and clean the separatory funnel as soon as you have finished with it. Label all solutions immediately. Keep both solutions until you have isolated your organic product. A common problem encountered during extraction is the formation of emulsions. An emulsion will form when droplets of one solution become suspended in another, and the suspension will not separate by gravity. Emulsions often form in extractions involving basic solutions such as sodium hydroxide, or from shaking the funnel too vigorously. Sometimes the emulsion clears if the funnel is left undisturbed for a few minutes. However, most emulsions are more persistent, and prevention is the best cure. If an emulsion forms despite precautions, it must be broken to efficiently recover the product. Use several drops of saturated salt solution or methanol, or vacuum filter, or allow the emulsion to break while standing. Salts are generally soluble in water. This property makes it possible to separate acidic or basic organic compounds from neutral compounds using liquid-liquid extraction. Let us watch the change in color with the change in solubility of the indicator 2,6-dichloroindophenol. In its neutral form, it is a weak acid and is colored red when dissolved in organic solvent. When this indicator is treated in aqueous base, it forms a salt and dissolves in the aqueous solution. The salt form, the anion, is blue. In this separatory funnel, we have water, the top layer, and chloroform, the bottom layer. The interface is difficult to see. If we add the acid-base indicator, the sodium salt of 2,6-dichloroindophenol, it turns the water blue, indicating that this salt is water-soluble. Now add dilute hydrochloric acid to change the pH below 7, that is, to make an acidic solution. The solution turns to red upon swirling. After shaking the phases together, the salt form of the indicator is neutralized to its red phenolic form. The phenol form is more soluble in chloroform, as indicated by the red color moving to the lower layer. If dilute sodium hydroxide solution is added carefully and the mixture shaken once, as you can see, part of the indicator is changed to its anionic form as indicated by the return of the blue coloration in the upper water layer, and part of the indicator remains acidic as seen by the lower red chloroform layer. Continued shaking changes all of the indicator to its anionic form, and once again the aqueous layer becomes blue while the chloroform layer is nearly colorless. The formation of the salts of an organic acid or organic base changes solubility properties. Change in solubility behavior allows acidic, basic, and neutral organic compounds to be separated using liquid-liquid extraction in a separatory funnel.